Hello friends, welcome back to another video tutorial. Today's topic is Janus-particles. Among many other nanoparticles systems, Janus-particles have recently attracted a lot of attention as the next generation smart nanomaterials, due to their complexity and flexibility in structures and properties with their potential application, particularly in biomedicine. In this tutorial, I will explain in more detail about Janus-particles, types, different synthesis methods and finally applications of Janus-particles. Janus-particles are particles with two or more sides that have different surface chemical compositions or polarities, or are made up of two components that have different geometrical morphologies. Janus-particles, named after a two-faced Roman god of the same name, were suggested by Pierre-Gilles Lejeune when he made his Nobel laureate speech to the scientific community in 1991. The most typical Janus particle is a sphere with one hydrophobic half and one hydrophilic half the other half. Janus particles, strictly speaking, have a 50:50 distinct coverage in shape, composition, chemistry, polarity, and other properties of importance. These particles have fascinating properties and functional asymmetry. It can be anisotropic in surface chemistry and or in shape. If one hemisphere is hydrophilic, the other is hydrophobic. If one hemisphere has a negative charge, the other has a positive charge. Types of Janus particles. Janus particles can be divided into two types on a macroscopic level, such as patchy Janus particles and compartment Janus particles. Patchy particles are defined as structures with several phase-separated domains in the core, whereas compartmented particles are characterized as structures with finely regulated patches of variable surface. Janus particles can be formed into spheres, rods, discs, bars, tubes, dumbbell-shaped, half-raspberry-shaped, disc-shaped, hamburger-shaped, acorn-shaped, snowman-shaped, ellipsoids, cylindrical, and more complicated shapes. Synthesis of Janus particles. Janus particles were created in the beginning by breaking particles into segments. The shape, size, and purity of the heterogeneous particles were obtained with little control. Many approaches for fabricating Janus particles have been explored in recent years. They can be broken down into three categories: masking, bottom-up assemblies, and controlled phase separation. Masking was the first technique used to create Janus particles. This approach was developed by simply changing the unprotected side and removing the protection. The size of the first generation of big heterogeneous particles has now been reduced to the nanoscale. The masking technique consists of 4 steps. To begin, homogeneous nanoparticles are trapped at a surface, exposing one hemisphere. Second, a chemical acts as a masking agent and covers them. Third, that chemical alters their characteristics. The masking agent is then removed, allowing Janus particles to be released. Bottom-up assemblies. This method produces monomolecular Janus nanoparticles. The nature of the branching point, the number of primary branches, the density of radial branches, and the distribution of chemical moieties inside or on the surface of the macromolecule are the factors that control the properties of these materials. Next is controlled phase separation. In this method, two incompatible substances were mixed to form a perfect mixture, and then separated into their own domains, while still being part of a single nanoparticle. The evaporation of the solubilizing solvent is the most useful trigger, but controlled separation can also be achieved after in situ polymerization. Biomedical application of Janus particles. Janus particles that combine different functional materials into a single unit and are capable of diverse composition and surface chemistry have been shown to perform well in different biomedical applications such as imaging, drug delivery, biosensing and tissue engineering. Janus particles for imaging application. Janus nanoparticles have the advantage of having two distinct faces, which not only allow for two complementary imaging modalities but also provide two functional surfaces for the attachment of various types of molecules, making them particularly appealing as multifunctional probes. See the figure of Fe3O4 nanodumbbells, dumbbell-shaped inorganic Janus nanoparticles, have also received a lot of attention as multifunctional probes for diagnostic and therapeutic applications. This synergistic effect observed when O and Fe3O4 were present in the same particle. More importantly, when the N nanoparticles were intravenously injected into mice model, They demonstrated dual contrast capability. Janus particles are also used in biosensing applications. Janus particles have been developed as biosensors in addition to therapeutic and in vivo imaging applications. To provide binding sites for analytes, the surfaces of these nanoparticles are commonly functionalized with large biomolecules such as proteins or DNA. The presence of these biomolecules on particle surfaces, on the other hand, can sometimes interfere with sensing functions and reduce their efficacy. Janus particles with two distinct faces and properties may offer elegant solutions for decoupling binding and sensing functions in these biosensors. Tissue engineering with Janus nanoparticles. Because of their numerous unique properties, various nanoparticles and hybrid materials are getting popularity for use in tissue regeneration. Because of their tunable composition, shape, and versatility in chemical functionality on different sites, particles with broken symmetry have a promising future for controlled cell growth and developing tissue scaffolds. It should be noted, however, that very few attempts have been made thus far to investigate the potential of actual nanometer-size Janus nanoparticles for tissue regeneration. Thank you for watching this video tutorial. If you like this tutorial, please share with your friends and colleagues. Thank you.